So we've seen where if the bases were the same for exponentials and logs, how we can solve them using our log properties, using exponential properties of equality and things like that. But what we need to look at is now, what do we do when exponentials and logs have different bases? How can we go about solving those? So for instance, like just to bring back up something we've already looked at, we've looked at if we had something like this, 2 to the x equals 8. We've talked about how we can take and rewrite 8 as 2 to the third, and then we can drop those bases and set those exponents equal. So when we can't do this, when the bases are not able to be written the same, maybe in an instance like something like this, 4 to the x equals 12. All right, if we have something like this, how can we go about solving this type of equation to help us get x when you can't get the bases to be the same? So a couple of things here, write down a couple of points. So when exponentials cannot be written with the same base, then we will use, or we will do, the inverse which is to take the log of both sides of the equation. And so that's one way we can go about being able to solve that equation, is to take the log of both sides. This allows us to use the power property for logs to continue solving the equation. And so that's one way we can go about it, is when we cannot get them to written with the same base, we can take the log of both sides, then use the power property for logs that we talked about yesterday to continue solving that equation. So if we go back to that example that we just had there, 4 to the x equals 12. If I'm going to take the log of both sides, which again is the inverse of exponential, it would look something like this. We would have log of 4 to the x equals log of 12. So we literally just did the log of both sides, because remember, anytime you're solving any type of equation, what you do to one side, you have to do the other to keep the equation balanced. So taking the log of both sides allows us to do that. Then we are allowed to use that power property that we talked about yesterday that says that we can then bring that exponent down in front of that log. And that's going to give us x log 4 equals log 12. And then if we want to get that x by itself, all I have to do is get rid of that log 4, which I can divide by it. And then we would be able to go into our calculator in Desmos, whatever it is you prefer, and we would be able to do log of 12 divided by log of 4. And so I'll bring it up here in Desmos for us to look at. So you can go under your keyboard, under Desmos and under functions, And you can find your logs here under where it says calculus, but you can also just go in and type in log and it'll allow you. Now, the one thing I will say about that is if your base is different, it's not a base 10 log, then you would have to come in here and actually use the one that's in function so that you could get that base to change. And you'd have that cursor down there for you to be able to do that. But since we're just doing regular log base 10 log, then we can just simply type in log and we could type it in log of 12 divided by log of 4. All right, and in these situations, I'm going to encourage you to round to the nearest hundredth. All right, so in this case, that would be 1.79. So 1.79. All right, so that's one way you could go about solving that. All right, the other way that we could go about solving that same type of equation is to change it to logarithmic form with our loggy froggy. So if we take that same example, so 4 to the x equals 12, right? And as we talked about the other day, how to convert something from logarithmic form to exponential and vice versa, we can do the same thing here. We can take this exponential, we can change it to log form, and we can solve it that way. So we start at our base, we go to 12, and then to x. So that would be, we got log, we started at 4, our base, then we went to 12, and then we landed on x, so that's what we're equal to. So then I could go back into Desmos and I could type in exactly what you see there, log base 4 of 12, and we should get the same answer. So 2 different ways to go about doing this. All right, let's see what we get when we type this in. This is where like I was telling you, it's going to be best in your case to go under that functions menu and select the one that has the base A log. So you can change that to a 4 and then type in 12. All right, and you can see there, yes, indeed, if we do log base 4 of 12, we do indeed get the same answer, 1.79. And so again, 2 different ways that you could go about solving those equations when your bases are not the same. So if we want to write down another way, you can solve exponential equations when bases are different is using loggy froggy to rewrite the exponential in logarithmic form. All right, so either way you want to go about doing that. And talking about solving log equations. When you cannot use property of equality. How do we solve log equations when we cannot use the property of equality? So when we cannot use the property of equality, with logs, because we do not have logs on both sides of the equation. Then use loggy froggy. So again, that's coming up, loggy froggy, to change the log to exponential form. To help you solve the equation. And so when we cannot use that property of equality because we do not have logs on both sides of the equation, then use loggy froggy to change the log to an exponential form to help you solve the equation. And so we can go through an example of how this would work as well. And so just a quick example. So if we have log base x of 81 equals 2. So you can clearly see we do not have logs on both sides, so we cannot just drop the logs and set the rest of it equal. Can't use that property of equality. So we're going to go to that loggy froggy and change this to an exponential form, so that then that might help us to solve this equation. So we're going to go start it here at base x. We're going to go to 2 and then to 81. So we started at our base of x, went to 2, landed on 81, so that's what we're equal to. So now looking at this exponential equation, x squared equals 81, this is an exponential equation that I should be able to easily solve. Right? Because remember we talked about inverses the other day. The inverse of a squared is to take the square root of it. So I could take the square root of both sides here. And that's going to allow that square root and square to cancel each other out, leaving us with just x. And then the square root of 81, hopefully we know that, that is 9. So we can get x equals 9. And so just a simple example there of how you can use that loggy froggy again to change something that is in log form to exponential to help you solve. Now before we continue on doing some solving with these exponential and logarithmic equations that don't have the same base, I want to kind of pause from that for a moment and talk about not only do we have just exponentials and logs, but you also have specific or special types of exponentials and logs, and those come in the form of base E exponentials and natural logs. And so take a couple minutes here and we're going to talk about base E and natural logs, all right, because these types of problems can also come up in our solving with exponentials and natural logs. So base E, when we talk about base E exponential, we are talking about an exponential function that instead of having like a base B, its base is actually going to be E. All right, and where E is an irrational number. All right, so E is not a variable here. E is the irrational number, E, right? And it is approximately equal to 2.7182.81828, and then it kind of keeps going on from there. So it's like pi in that it's an irrational number that does not stop, that does not terminate. So this is what we're talking about here. Instead of having a base B, where B could be like 2, 3, 4, something like that, the base in this case is E, which is an irrational number. The inverse of base E is natural log. So like regular exponentials and logs are inverses of one another, base E also has an inverse, and that comes in the form of natural log. All right, when you see us write it, you're going to see us write it as LN. LN stands for natural log. LN stands for natural log. One other point I'll make here is that all properties of log, so just your regular logs, will work for natural log. So all those properties we looked at yesterday will work for ln or natural log as well. So your power property, product, quotient, all those things where you could rewrite it in the different forms, all of those are appropriate and can be used for natural log as well. And so that was just a little bit about natural log and base E. Again, they are direct inverses of one another. They will cancel each other out. You'll probably find that you actually like problems that involve base E and natural log a lot more than you do with other exponentials and other logs. I mean, most students like those because they easily cancel each other out. And we'll get into that when we start looking at some examples. But I just want to talk about those because we will have some come up in the next couple of examples that we're going to look at. All right, so let's just get into solving some more problems. So we're going to say solve, if needed, round to the nearest hundredth. So we're talking about rounding to the second decimal place. All right, so these are all going to be kind of mixed up. Some will be regular exponentials and regular logs. Some of them will be base E and natural logs as well. All right, so you got two ways that you could go about solving this one. All right, we talked about you could take the log of both sides and solve it that way, or you could use Loggy Froggy and change it to log form and solve it that way. I will show both ways as we go through and do a couple of these, and then I'll kind of stop and just pick one of the ways to go about doing it. But if you prefer the other way, then you're welcome to go about and continue doing it by doing that. So starting out, if we take the log of both sides. So log of both sides. That allows us then to use that power property and take that exponent and drop it down in front. And then our ultimate goal is to get that y by itself, so we can do this in one fell swoop all right, because all of these things, the 2, the y, and the log base 4, or the log 4, are all multiplied by one another, all right? And if we do the opposite of multiplication, that is to divide on both sides. So I can do it in one division if I divide by 2 and the log 4. Divide by 2 and log 4. At one time, those are going to cancel out, leaving us with just that y on the left-hand side. And then we can go to our calculator, we can go to Desmos and type in log 10 divided by 2 log 4. Log 10 divided by 2 log 4. So let's see. Log 10, close the parentheses, divided by 2 log 4. All right, and again, we're going to round to the nearest hundredth here, so that would be 0.83. 0.83. All right, so that was showing you by taking the log of both sides. The other option to solve the same equation, right, would be to change it to logarithmic form, doing loggy froggy. So starting at the base 4, we go to 10, and then to 2y. So this is going to be log base 4, then we went to 10, and then we landed on 2y, so that's what we're equal to. Again, our goal is to get that y by itself. So do we want to get rid of that 2 by dividing by 2? And we can go to calculator Desmos and type in log base 4 of 10 divided by 2, and we should come up with the same answer that we had for the previous one. So let's see here. I'll clear that one out. So this is going to be, I'm going to go under functions. Go select the one with log base A, and this is 4 of 10, then divided by 2. And indeed, we do get the same answer there, 0.83. 0.83. Right, so again, it does not bother me which way you decide to do it. Right, you've got both of those as options. Right, taking the log of both sides or doing loggy froggy. Right, let's look at another one. 10 to the x minus 2 equals 35. So just to kind of reemphasize, why are we doing it this way? Remember that these are the cases where you cannot get that same base on both sides to drop those bases, right? So you cannot get same base on both sides to drop those bases. So I'll show it again, how we do it if we did the log of both sides. And I'll show it as if we did loggy froggy. And again, you can make that decision on what you feel like is what you like best. So then we can use that power property, bring that x minus 2 down in front, and I am going to write that in parentheses. Okay, and it's x minus 2 times log base 10, right? But we can get rid of the log 10 by dividing it, because it is multiplication. And then x minus 2 comes down. And then still we're trying to get that x by itself, so now I'm going to go plus 2 on both sides. And then we're going to go to the calculator and type in log of 35 divided by log of 10, and then do plus 2 and see what we get. Log of 35 divided by log of 10. And then we're going to do plus 2. Plus 2. Log of 35 divided by log of 10 plus 2. All right, make sure you move that cursor out away from underneath that division sign before you hit plus 2. And again, we're going nearest hundredth, so this would be 3.54. 3.54. If I had done Loggy Froggy with this one, find a very similar way to go about doing these. So start at our base 10, go to 35, and then to x minus 2. So this would be log, started at 10, went to 35, landed on x minus 2. Now in this case, I would probably go in and I would figure out what is log base 10 of 35, all right? And I'm not going to round it, and then I'm going to add the 2 after that. So let's go in Desmos again, go under functions, get the log with the base of a, so log base 10 of 35, oops. There we go. All right, and again, I'm not going to round any of that. All right, I would keep all of those decimal places. All right, and then I wouldn't round until you got to then adding 2 to that. Right, or if you feel good and comfortable with how to put things in Desmos, right, put all of that in parentheses, and then you could do plus 2. Put that whole thing, log base 10 of 35 in parentheses, and then doing plus 2. And so if I hadn't rounded it, I would have kept all those decimals. 1.5440680044, and then I would go plus 2 on both sides. And see, again, we get the same answer, 3.54. All right, so again, showing you both ways. You make the decision on what it is you like best, whether you like taking the log of both sides or whether you like doing Loggy Froggy. All right, our next one here. We're going to introduce some of those base E and natural log ones. So this is e to the x equals 7. E to the x equals 7. So again, I think you're going to find that you probably like these a lot better than some of the other ones we've looked at because base E and natural log, again, are direct inverses of one another. So when it comes to getting rid of that E right there, right, all I have to do is the inverse of it, which is to take the natural log of both sides, which, unlike with exponential base log and things like that, natural log and base E automatically cancel each other out, which allows you to then drop that x down, and then all you have to do is figure out what is the natural log of 7. right, in this particular case. So unlike with when we take the log of both sides or you do log frog, you have to do more work with like that. When you have a natural log and you have that base e there, once that e is by itself, it will directly cancel out with that natural log, and that'll allow you then to figure out what x equals. So natural log, again, you can go under functions, or you can simply type it in. All right, there it is under functions, or you can just type in ln. All right, and Desmos will know what you're telling it to do. And you're going to go to the nearest hundredth. So second decimal is a 4, behind it is a 5, so that's going to round that 4 up to a 5. So 1.95. 1.95. We'll look at another one with that base e. We have 3e to the 0.25x equals 45. Now you can't take that natural log until that e is by itself. The e has to be by itself before you can take the natural log. So with that being said, I have to get rid of that 3 first by dividing, because it's 3 times that. 45 divided by 3 is 15. And now at this point, I can take the natural log of both sides to get rid of that e. Right, but it's not until I have that e by itself that I can do that. So then that natural log, that e would cancel each other out. It allows that exponent to drop down. And then we're trying to get that x by itself. So if I want to get rid of that 0.25, I will divide. And I'm going to go to the calculator, Desmos, and type in natural log of 15 divided by 0.25. Natural log of 15 divided by 0.25. And again, we're going nearest hundredth. So look at that second decimal. It's a 3. Behind it is a 2. That's not going to round it any different. So we're going 10.83. 10.83. One more here with this base E, and I would encourage you at this time to pause the video and try this one on your own, and then come back and see how you did. So again, pause your video at this time and then come back and see how you did on this one, solving it using natural logs for that base E. And so hopefully you paused your video, then you came back and you watched how I came up with 2.20. We're going to take a step away from doing some of those natural log and base E for a second and go back to some logs that do not have the same base, or where we can't simply use property of equality. And so here in this example, we do not have logs on both sides, so we cannot just simply drop those base logs on each side. We said that our way to go about this when we could not drop those bases with that property of equality was to use loggy froggy to change it to an exponential to help us solve. So start in my base 2, come around to 4, and then x plus 4. So we started at 2, went to 4, that's our exponent, landed on x plus 4, so that's what we're equal to. And so now looking at this, you have 2 to the 4th. That is something that we can actually figure out what it equals. All right, and then it's going to be just a simple linear equation at that point solving for x. So 2 to the 4th is 16. And then we'll subtract 4 from both sides. And we get x is 12. So situations where we cannot take the log, cannot just drop the logs on both sides because we only have one of them, we'll do loggy froggy to help us get it into an exponential form, which then is going to allow us to solve for x. We'll do another one like this. So again, we do not have logs on both sides, so we cannot use that property of equality to just cancel out those logs. So we're going to have to take and do loggy froggy, starting at x, our base. Okay, and then do that loggy froggy to then be able to change it to an exponential. So x is where we started, that's our base. Then we went to 4, that's our exponent. And then we landed on 1024 is what we're equal to. Now this one is a little bit different than the previous one in that x to the 4th is not something we can simply plug into the calculator. But if it had been an x squared, let's say for instance, then you would have said, oh, it's an x squared, then I could take the square root to get rid of that squared. If I use that same logic, right, this time it is the 4th power, that means that I can do the 4th root of both sides to have it cancel out with that exponent. So just like with x squared, take the 4th root, and that allows you to then figure out what is the 4th root of 1024. So we can go into Desmos and we can figure out that. Right? You are going to want to go under your functions. Oh, there it is. Under down there at the very bottom is under number theory. That's where you see the one where you can change that index to a number other than 2. So we're going to change that index to a 4. And then underneath we'll do 1024. And again, we're going to the nearest hundredth. So I go to that second decimal place and I see a 5. And then I look behind it and there's a 6. So that 6 is going to round up the 5 to a 6. So we're going to end up with 5.66. 5.66. All right, so if you need some time, just take and process these. You can pause at any point. All right, I'm going to keep going with some more examples, and we're going to do some here with some natural logs. So if we have natural log of 2x minus 7 equals 0. And so kind of like with base E, in order to use the inverse of natural log, which is base E, you have to have that natural log be by itself before you can start using base e to get rid of it. So in this particular case, that means I need natural log of 2x by itself before I can use that base e to get rid of that natural log. So that means I need to add 7 to both sides. And then at this point, because natural log is now by itself, to get rid of a natural log is to do base e on both sides, which allows e and natural log to cancel each other out, and that 2x comes down. And then on that right hand side, we have e to the 7th. And we want to get that x by itself, so it's 2 times x, so I do the opposite there and I divide. And we can have e to the 7th divided by 2. E to the 7th divided by 2. E raised to the 7th. Oops, I need to do that. And then do divided by 2. E to the 7th divided by 2. Nearest hundredth, I see the 1. I look behind it, it's a 6. So that's going to round that 1 up to a 2. So 548.32. 548.32. And I will take this time to say I apologize if you hear my dog in the background. She is snoring right next to me, and I apologize for that. Maybe it'll add to your notes and have some entertainment for you. All right, let's look at another one that involves that natural log. I will go back and say the reason that we couldn't use that property of equality with these natural logs on that first one there in H was again because you don't have natural logs on both sides. Right? You don't have natural logs on both sides that you can eliminate. It has to be one on each side for that property of equality to work, right? Which we did not have in this case. All right, so going on here to I. You remember we did say that all those properties that we had for regular log logs, those can also be used for natural logs. So with that being said here, I see that we have two natural logs separated by addition. If we think back to what we said for log and the product property, we said that if we had 2 logs separated by addition, then we could rewrite it as a single log if we used multiplication. So that's what we're going to do here on this left-hand side. I'm going to rewrite that as 4x times x to combine it down to just 1 log. Because remember, you can't do anything with any bases or any logs unless you have one of them. We have to have one. So then we have to use those properties to simplify them down to get them to where we have 1 log or 1 exponential before we can use some of those other properties. So this is going to give us natural log of 4x squared. And once I have that, then it's that 1 natural log's by itself. So then to get rid of it, I do base e on both sides, which allows that natural log and that base e to cancel each other out, and that 4x squared to come down. Yeah, and then we're solving for x at this point. I want to get rid of that 4 by dividing. Yeah, and then get rid of that squared by taking the square root. And we can go to Desmos or a calculator and put that in. Square root of e to the 9th divided by 4. Square root of e to the 9th divided by 4. And then we're going nearest hundredth once again. The second place is a 0. I look behind it is an 8, so that's going to round that 0 up to a 1. 45.01. Here's another one involving that natural log. And so in this particular one, the natural log is already by itself. All right, so we can go ahead at this point and do base E to get rid of it. Base E and natural log cancel each other out. Allows that x minus 1 to the third power to come down. And then gives us e to the 8th on that right-hand side. Okay, and then we're still trying to get that x by itself. So think about it. What can get rid of something to the third power? If it had been squared, you would have done square root, but it's third power, so we want to do cube root. So cube root of both sides. X minus 1 comes down. We have cube root of e to the 8th. And then we want that x by itself, so I can go plus 1. Yeah, and then we can put all of that stuff you see there on the right-hand side in Desmos or our calculator. Cube root of e to the 8th, and then we'll go plus 1. Cube root of e to the 8th plus 1. So, functions. Go down to the bottom, get that where you can change that index to a cubed. Then type in e to the 8th. And make sure your cursor goes outside of that radical before you add in plus 1. So cube root of e to the 8th plus 1, 15.39. Okay, this is K. And we're going to go back to doing a couple with log log. So again, why do we have to use log? We don't have logs on both sides of the equation, so we can't simply use that property of equality like you might have done the day before. Right, so we do, or we can use that product property though, and we can rewrite that left-hand side as a single log if we use multiplication. Right, so using that product property to rewrite that left-hand side as a single log using multiplication because of that addition sign you see in between there. This is going to mean that we're going to have to FOIL those two together. So x times x is going to be x squared. X times -3 is -3x. X times 2 is 2x. And then 2 times -3 is going to be -6. Combine those like terms. Gets a negative x. And so again, you can see we do not have logs on both sides, so we cannot use that property of equality there. When we can't use the property of equality with our logs, then our option there is to go loggy froggy. So we're going to start our base 6, jump all the way over here to 1, whoops, and then over to x squared minus x minus 6. So we started at 6, that was our base. We went to 1, and then we landed on x squared minus x minus 6. So that's what we're equal to. 6 to the first power is 6. Okay, now this is a quadratic, right? Most of the time you're going to try to solve quadratics by factoring. If I'm going to try to solve this quadratic by factoring, I need to have everything on the same side. So I need to move that 6 over to the other side. Yeah, and then there you can see we get x squared minus x minus 12. And this is something we would try to factor. We need two numbers that if we multiply them, we get negative 12. If we take the same two numbers and we add them together, we get negative 1. So multiply, get negative 12, add them, and we get negative 1. I believe that is negative 4 and 3. We can take each of those now that they're factored, set them equal to 0 to solve them. This first one's going to give us x equals 4. That was supposed to be plus 3. Plus 3. There we go. So negative 4 and positive 3. This one's going to give us negative 3. All right, and then this brings up a point here. When you get a negative, right, especially when you get negatives, right, it's going to be very important that you go back and you plug that in to your original equation and see if that has you taking the log of a negative number. All right, so if I go back up here to the top to where we started, if I plug in a negative 3 here or here, that's going to give me log base 6. In the first one, that's going to be a negative 1 there. And then it would be, the second one would be log base 6 of negative 6. You cannot take the log of a negative number. You cannot take the log of a negative number. So since that is true, since when I plugged it in, it gave me the log of a negative number, that tells me right here that negative 3 is not going to be a solution that I can use in my problem. It's an extraneous solution, one that doesn't work, right? But if I plug in 4 in either one of those places, so 4 here or here, that's fine. In both of those cases, that gives me positive numbers there. So I'm able to do that. I can take log of positive numbers, but I cannot take log of negative numbers. All right, so that's why negative 3 did not work. So we only have one solution here, and that is x equals 4. All right, so I know that was a lot of examples. If you need to go back and watch some of them again, by all means do that. And then you can go ahead and start on your next assignment.